First of all, a big thank you to the organizers. It's a wonderful meeting. Big thank you for putting this together. I'm not an expert in Koopman methods, but I think what I'm going to talk about has a lot of overlap with the things that are being discussed. So in the first 5 minutes or so, I will give you an overview of the kind of things that we are dealing with. And so the starting point is the Hamiltonian of the complete system of interacting electrons and nuclei. So this is non-relativistic Schrödinger equation, or weakly relativistic if you include spin-orbit coupling. So we have the kinetic energy of the nuclei, kinetic energy of the electrons, nuclear-nuclear Coulomb repulsion, electron-electron Coulomb repulsion, and the electron-nuclear attraction. And in what follows, I will always use this notation of little r double underline for the set of electronic coordinates and capital R double underline for the set of nuclear coordinates. Now, with this Hamiltonian, we think of solving the time-dependent Schrödinger equation with or without an external laser field, which is usually given as a classical field. Okay, so that's the problem. So the solution of this equation is the ultimate truth for our case, and there's a standard way of dealing with this problem, and the standard way involves 2 steps. First step is to solve the electronic structure problem in Born Oppenheimer approximation. So from the previous Hamiltonian, we drop the kinetic energy of the nuclei. So we are left with this Hamiltonian, where the nuclear coordinates only appear as parameters. And we imagine we solve this correlated many-electron problem for all possible nuclear configurations. So the eigenfunctions, the Born Oppenheimer eigenfunctions and the corresponding eigenvalues are then functions of the nuclear coordinates. So this is a cartoon of these so-called Born Oppenheimer surfaces. Okay, that was the first step. This, so to say, creates a basis of the electronic Hilbert space. And then we expand the full electron-nuclear wave function, or the solution of the time-dependent Schrödinger equation that I showed you on the first slide. We expand that in the complete set of Born Oppenheimer states. And it's a slightly tricky thing because these Born Oppenheimer states also depend on the nuclear coordinates parametrically. And we choose here the same nuclear coordinate, right? That's a choice. Then the expansion coefficients inevitably depend on the nuclear coordinates and on time. And if you plug this back into the time-dependent Schrödinger equation and multiply from the left with the Born Oppenheimer states, we end up with this coupled set of equations for these coefficient functions. So what appears here is the so-called non-adiabatic couplings. So those are weird objects. You have a nuclear momentum operator, so derivative of the Born Oppenheimer wave functions with respect to the subscript, so with respect to the parametric dependence, first order and second order non-adiabatic couplings. Now, these objects here are functions of the nuclear coordinates, and if you are far away from conical intersections and avoided crossings, then these guys are very small, exponentially small, in fact. And if you're in a region in nuclear configuration space where those guys are small, so these terms are negligibly small, we can neglect them, and we are left with something very nice, namely just the first line, which is a time-dependent Schrödinger equation for just the nuclei for this coefficient function, moving in one and only one potential energy surface. So this is what we get if we neglect the non-adiabatic couplings. So this is that one Born Oppenheimer surface, and we have a nuclear wave packet moving forth and back here. And the wave function is then given by this one term, right? So of the expansion, the Born-Wang expansion, only one term is left, namely this Born Oppenheimer state at all nuclear configurations times this wave packet. This wave function is called adiabatic approximation, right? And it's useful to remember that essentially in all calculations of vibrational spectra, one always makes this adiabatic approximation, and in addition, one usually makes the harmonic approximation where one approximates this by a parabola, but it's two separate and very distinct approximations. Usually this is super good, this kind of approximations, but not always. You can imagine if there are two important Born Oppenheimer surfaces very close to each other here near the minimum, then it's clear that with the red surface alone, you cannot calculate the vibrational spectrum. You need to include the blue one as well. So this gives you a quantitative change. But there are even more dramatic failures of the adiabatic approximation, and I'm going to show you two of them. First one is a situation where you have two important Born Oppenheimer surfaces and all the others are far away, let's say, energetically. So then the approximation in this regime would be two contributions from the Born-Wang expansion corresponding to these two Born Oppenheimer surfaces. And then the nuclear density consists of these two parts, right? If you take the full electron-nuclear wave function in this approximation, take absolute square and integrate out the electronic coordinates, you get these two parts of the nuclear n-body density. And so if we had only the blue surface, this is the case that I discussed a minute ago, then we would just oscillate here forth and back. But then these non-adiabatic couplings are large here in the vicinity of the avoided crossing. So whenever this blue wave packet crosses this region, then these non-adiabatic couplings create a contribution of this red surface. And this happens periodically, whenever this guy crosses the non-adiabatic region here. So periodically, there's a little red hump going out. And the case that I showed you here is for sodium iodide. It's a very famous case, where the red surface asymptotically corresponds to neutral fragments. So you would expect that neutral sodium atoms come out periodically, and those can actually be measured in pump probe experiments, and you can nicely read off here the periodicity of that underlying blue oscillation. Now, if you start here at a different place in the upper surface with a different initial condition, and you can do this with a different initial femtosecond laser pulse, then the oscillation period will be different. So you can actually map out, so to say, the upper potential energy surface. So this is the famous experiments of Ahmed Zewail, who got the Nobel Prize for this in 1999. So everything is perfectly understood. But it's clear, you cannot describe this with one surface, no way, right? The whole effect comes from the fact that you have two surfaces. So this is a complete breakdown of the adiabatic approximation, you could say. Now, a very different kind of breakdown is when we look at local electronic current densities that are associated with nuclear motion. So think of a vibration or something like an isomerization, so slow nuclear motion. And you ask yourself, what do the electrons do? Well, what you expect is they move together with the nuclei. Now, if you want to describe this local electronic current within the adiabatic approximation, you could first calculate the time-dependent density, so plugging the absolute square of this in here and integrating out the nuclear degrees of freedom, that will give you the time-dependent electronic density. And this is indeed very close to the true time-dependent density. But then if you try to do the same thing with the electronic current density, right? So you evaluate the expectation value of the current density operator, what you get here is the imaginary part of this object with respect to the Born Oppenheimer states. But usually, think of the lowest Born Oppenheimer state, they are real valued. There is no imaginary part. So, unless they are degeneracies, that's a different story. They are real valued, so the current is zero. But it can't be zero. We know it can't be zero. The electrons move with the nuclei. So it's totally wrong. So this is two cases of failures. Now, when we are in such a situation of non-adiabaticity, as we say, when the adiabatic approximation fails, what can we do? Well, in principle, one has to go back to the Born-Huang expansion. Now, when only two or a few, let's say, surfaces are important, like in the Zewail experiment, then that's feasible. But if you think of big systems, big molecules, solids even, or this case of the electronic current density, where it turns out that you have, when you try to calculate it, many, many contributions, all very small, from many Born Oppenheimer states, it's very, very hard to do. So we are going to address in this talk situations of this kind. Now, one ultimately wants to treat nuclear motion in one way or another with classical trajectories. Right? That's more efficient than the quantum problem. But then, if we want to treat this kind of non-adiabaticity, you immediately have a problem. Right? Think of the Zewail experiment. Right? What is actually the proper classical force when the nuclear wave packet splits, like here? Is it the gradient of the upper surface or the gradient of the lower surface? Algorithms like Ehrenfest dynamics actually work with an average of the forces from the two surfaces, which is totally unphysical. And for these reasons, as you know, algorithms like surface hopping have been invented. But it's a well-defined question. What is actually the true classical force when the nuclear wave packet splits? And as I will show you, that that's one important message of my talk. There is actually only one correct answer up to within a gauge transformation. There's only one correct classical nuclear force. Okay, and the way we do this is with what we call the exact factorization. It is essentially an exactification of the adiabatic approximation. So you remember the adiabatic approximation was one Born Oppenheimer state, one single for all capital R, times a nuclear wave packet. And one can make this exact by allowing this electronic amplitude to be something more general. So it's not the Born Oppenheimer state, but something more general. It shares with Born Oppenheimer the feature that its absolute square integrated over the electronic coordinates is 1, so it's normalized for each fixed capital R. So it's something like a conditional amplitude, but it's not the same, right? But that aspect is a common feature. And one can represent the full electron-nuclear wave function in this way. So the philosophy that we are following is basically to start from that full quantum mechanical problem and then rewrite this full quantum mechanical problem as two problems. One Schrödinger equation for the electrons that parametrically depends on the nuclei, and one Schrödinger equation for only the nuclei. And this can be done without approximation. That's the exact factorization. And then, only then, we make classical, semi-classical, or similar approximations, treating the nuclei with trajectories. So that's the philosophy. So here's the outline. I will first show you this theorem. And the equations of motion for these two factors lead to a concept of what could be called an exact and unique time-dependent potential energy surface and a time-dependent vector potential, which has the structure of a Berry connection. Then I will come back to this problem that I just mentioned, the calculation of local electronic currents that are associated with nuclear motion. And then I come to the main part of the talk, namely quantum classical algorithms, to describe this kind of non-adiabatic dynamics. Finally, I will discuss in more detail the role of the vector potential. So before I start, I want to thank all the people that did this work. Without them, nothing would have happened. So the factorization, these very general aspects were developed by Ali Abedi, that was his PhD thesis, together with Nipa Maitra in New York. And all this was based, so that's for the time-dependent case, was based on previous work by Nikitas Gidopoulos. So with him, this whole project got started almost 20 years ago by now, when he was postdoc in my group. He is now a professor in Durham in the UK. The mixed quantum classical algorithms, the main driving force was Federica Agostini and Seung-Kyu Min and Ivano Tavernelli at the Zurich IBM lab. Basile Curchot worked on this very interesting aspect of how interferences show up in this context. Then this question of electronic currents, that was the work of Axel Schild, Rodolphe Vuillemier, and Federica as well. And I will also discuss some Ehrenfest equations for the nuclear subsystem. This was developed by Chen Li, and the Berry phase aspects have been discussed by Seung-Kyu Min, Brian Request, and Andrea Nuolo. Okay, so now the first theorem. So this is again the full time-dependent Schrödinger equation. And I claim the solution of this can be written in this factorized form, where the only condition that we require is that the norm of this electronic factor is 1 for any fixed nuclear configuration and any fixed time. So that's the statement. If you think about it, this is actually kind of obvious. Think of the absolute square of that equation. So then the left-hand side is the joint probability of finding the electrons at little r and the nuclei at capital R. And this guy is the conditional probability of finding the electrons at little r given the nuclei are at capital R. And the absolute square of this is the probability of finding the nuclei at capital R. And this is a well-known statement of stochastics. Any joint probability can be written as a conditional probability times a marginal probability, and that's what this is, right? So it's the analog statement for the amplitudes. So you may worry a little bit about the phase, and I come back to this later, but it's kind of obvious that this should be true. And this actually has a long history, so it goes back to Jon von Neumann, who first tried to formulate quantum mechanics in terms of such conditional probabilities. He does it in a very general way, so the degrees of freedom are not necessarily the electronic and nuclear degrees of freedom, but he does it for general degrees of freedom. But it's the basic idea is there. And then for electrons and nuclei, this was worked out a bit more in 1975, and there's a few more papers on this. Strangely, nobody, to the best of my knowledge, actually had the idea of deducing equations of motion for the two factors. So this somehow didn't happen. And this is what you see here. So once you know that the full wave function can be written in this factorized form, you plug it into the Frankel variational principle and make the quantum mechanical action stationary with respect to variations of the two factors. That's all you do. And you include the normalization condition for each capital R of the electronic factor as a Lagrangian condition. And then after a little bit of algebra, you end up with these two equations. So let's first discuss a little bit the nuclear equation. So this is a nice Schrödinger equation, right? It has a vector potential and a scalar potential, but otherwise it's a nice time-dependent Schrödinger equation. So this determines the nuclear factor. Then the conditional electronic amplitude satisfies this equation. Now this is more complicated. First term here is the Born Oppenheimer Hamiltonian, and the other terms have a prefactor of 1 over the nuclear mass, or if you write it in dimensionless quantities, it's the ratio of electronic over nuclear mass. So you have a small parameter here, right? And you see immediately in the infinite nuclear mass limit, you're back to Born Oppenheimer, as one might expect. Okay, now these terms are weird. So here, first of all, there is the nuclear wave function appearing, so these two equations are coupled. And in addition, you have a nuclear momentum operator here, and it acts on the subscript, so on the parametric dependence of the electronic wave function. So, well, it's kind of weird, but that's what you get. So these two quantities that appear in the nuclear Schrödinger equation, the vector potential and the scalar potential, we call this the exact time-dependent potential energy surface and the exact time-dependent vector potential. So as opposed to the adiabatic approximation, I want to emphasize here, where we had a nuclear wave packet moving in a Born Oppenheimer surface. It's a bit similar, but this surface here is time-dependent itself. So we have a time-dependent scalar potential and time-dependent vector potential. Okay, now here comes a third theorem, namely, which also shows you what the vector potential and the scalar potential look like. So this is again the time-dependent nuclear Schrödinger equation. And what appears here as scalar potential and vector potential has to be calculated from the result of the electronic equation. So you really need to propagate these equations in parallel. And you see that this vector potential, the exact vector potential, has the structure of what is known as a Berry connection. And the time-dependent potential energy surface, the scalar potential, is given by a Born Oppenheimer part and these additional terms. So this is what you get. And the third theorem says that if you solve this nuclear equation with those potentials, then the density, the nuclear density, so when I use the word density, I always mean the diagonal. So it's the diagonal of the nuclear n-body density matrix, so the n-body probability density is given by chi squared. This I said already before, that's the marginal probability. But more surprising is that the nuclear n-body current density that is connected with this through a continuity equation, that is given by this expression. And this refers to the exact nuclear current density. So that's surprising. If you take a step back here, usually when we have a system that consists of two subsystems, and we want to calculate properties of a subsystem, for example, the nuclear current density, so that's a property, expectation value of the current density operator, then property of a subsystem, usually you need a density matrix for this. Not here. So the slightly surprising fact is that this nuclear Schrödinger equation alone, so that's a pure state, gives you the true nuclear current density that you would get if you took the full electron-nuclear wave function and calculated the nuclear current density by tracing out the electronic degrees of freedom. So here, this equation so gives you two things exactly: the nuclear n-body density and the nuclear n-body current density. So a few properties of these two equations of motion. First of all, this vector potential also appears in the electronic equation of motion, so this makes it a nonlinear equation in phi. Then these funny terms where you have a nuclear momentum operator acting on the subscript. Well, strictly speaking, this is not even an operator in the electronic Hilbert space. However, if you pretend it's an operator and you expand the electronic wave function in the Born Oppenheimer basis so that you can actually act with this nuclear momentum operator on the Born Oppenheimer states, then it turns out that this matrix is non-Hermitian. But you can prove that in spite of the fact that this matrix is non-Hermitian, the time propagation conserves the norm. And in the static limit, the eigenvalues are real valued. So it's a very specific case of non-hermiticity. Okay, and this I said already before, the two equations depend on each other. The nuclear wave function appears explicitly in the electronic one. Now, the nuclear equation of motion, it's a standard time-dependent Schrödinger equation, and you have a scalar potential and a vector potential, which are both n-body operators. Okay, so how do these time-dependent potential energy surfaces look like? And we take first a look at an example that is like the Zewail experiment. So you have a splitting of the nuclear wave packet. This is a simple example where you can solve everything exactly numerically. So it's an H2 plus model with soft Coulomb potentials in 1D. That's the initial nuclear wave packet. Here I plot the two lowest Born Oppenheimer surfaces just as a guide for the eye. So here you have an avoided crossing. And then we propagate the nuclear wave packet. And what you see here is the exact snapshots of the exact time-dependent surface. Right? So if you go a little bit further, I should also say these things here, this is just numerical noise, should be ignored. This happens at a place where the nuclear density is 10 to the minus 50, so this has no significance. So just look in the middle here. So now, as you expect, the nuclear wave packet splits. So that's the example that I had before. And then what you see here is that the exact time-dependent potential energy surface develops a step. Right? And you can actually prove that when the overlap of these two split-off parts of the nuclear wave packet becomes exponentially small, then this step becomes infinitely steep. Now, if you think of steps, right? What is the force? The force then jumps from the gradient of one surface to the gradient of the other surface. So this is very reminiscent of surface hopping. But what I'm showing you here is not surface hopping, right? It's just the exact time-dependent Schrödinger equation plotted in a slightly weird way. Okay, so now comes an important point. So as I emphasized before, these two equations of motion for the electronic factor and the nuclear factor respectively are totally equivalent to the full electron-nuclear Schrödinger equation. Right? So to solve those exactly, it doesn't make much sense. But the crucial advantage of writing the quantum mechanical problem in this way is that you have two separate equations, which allows you to do approximations for one and the other subsystem in a way that without knowing these equations, you would never dream of. For example, and this is, I just touched this very briefly. We have this small parameter, 1 over the nuclear mass, and it kind of offers itself to treat it in perturbation theory, first order perturbation theory. And so if you had not written down the equations in this way, that you would never get the idea of using this object in perturbation theory. And I should emphasize these terms in the red boxes, they include all non-adiabatic effects on the electrons, right? There is nothing else. This is all, because it's an exact equation for the electrons. So this is what we do. We treat this in first order perturbation theory. We look at a model system first, where we have a nuclear wave packet tunneling here through a barrier. And I'm going to show you, so this is simple given potentials so that you can solve everything exactly. And I'm going to show you here a snapshot that at which time of the snapshot, half of the nuclear wave packet has tunneled from one side to the other. So at this particular time, as you may expect, there's a nuclear current going through this barrier. Right? So current far away is 0, but there's a current here. And as one would expect, with this nuclear current, there's also electrons going through. If you plot the electronic current density, indeed, this is what you get. So this is the exact electronic current density. And sure enough, it goes from one side to the other, like the nuclear current density. Now, this was the quantity, remember, which in adiabatic approximation is strictly 0, right? You don't get anything in adiabatic approximation. Now, this first order perturbation theory, and that's what is shown here, gives you essentially perfect agreement. So this was a case, as I mentioned before, which is particularly hard because it involves many, if you do it in the Born expansion, many contributions, and all of them with a very small prefactor. So this is a tough problem, and writing things in this way gives you a really perfect answer. Where is this important? I just mentioned this in passing. It's important in vibrational circular dichroism, where the crucial quantity is the so-called rotational strength that involves a magnetic and an electric dipole. So, and this dipole has an electronic and a nuclear contribution, right? And it's clear from what I said before, in adiabatic approximation, the electronic contributions, this one being a linear current, this one being a circular current, they are strictly 0 in adiabatic approximation. And we then treat them in first order perturbation theory. And here's a comparison with other methods. I'm not going to dwell on that. So now the main topic. Again, we start from these two equations of motion that are still exact. But then we treat the nuclear motion with classical trajectories, keep the quantum treatment for the electrons. So here are these two equations of motion again. So we represent the solution of this in terms of nuclear trajectories. There's different ways of doing that. That's exactly what I will talk about in the coming minutes. And this is the electronic equation. Now, you should keep in mind that this electronic problem is still a correlated and electron problem. So that even by itself is very hard. But there is a whole toolbox of methods to deal with this. We take the simplest possibility. We density functionalize these equations. I'm going to show you how this is done in practice in a minute. So that's the basic idea. Now,
and you have 10 minutes left, or 5 plus 5.
That's perfect. Okay. So we start again from, here's again the equation. So that's the nuclear equation of motion. We rewrite it, the wave function in terms of absolute value and a phase, plug this in the Schrödinger equation, and since this is a standard Schrödinger equation, we get the usual equations that we have seen several times before. So you get a continuity equation for chi squared and this kind of Hamilton-Jacobi-like equation, where this is the famous Born or quantum potential. Now we solve this partial differential equation with the method of characteristics. So in the method of characteristics, one calculates curves, in our case that's the nuclear trajectories, along which the underlying partial differential equation, this one, becomes an ordinary differential equation. And so you represent these nuclear wave functions in terms of trajectories, the characteristics, and the equation that then these trajectories satisfy are Newton-like equations, and here they are written down. So this is the one. So r dot is the momentum, p dot is this object, and you see in the force that appears here on the right-hand side, there appears the time-dependent potential energy surface and the vector potential. But those have to be calculated from the electronic equation, remember. Now in the electronic equation, on the other hand, appears the nuclear wave function. So we have to somehow reconstruct from the characteristics, from these trajectories, the nuclear wave function. And I'm going to show you in a second how we do that. So we imagine we are now doing a Born expansion for the electronic factor, but only along the trajectories. So these coefficients then become purely time-dependent functions, and we have then ordinary differential equations. And what appears here is this vector potential along the trajectories. And what appears here is the term, a weird term that appears in the electronic equation of motion, which comes from this grad chi over chi term. That's this nuclear wave function, again, along the trajectories. And there's also the diagonal, non-diagonal, non-adiabatic coupling of first order. So this is what we need to propagate these quantities here. So how do we calculate this object, this what we call quantum momentum? Remember, the quantum potential has the Laplacian here. This is what we call quantum momentum, and this is what mediates the non-adiabaticity and in the electronic equation. So to evaluate this, as I said before, we need to somehow recover the nuclear wave function from the trajectories. And the way we do this is, well, we imagine that these trajectories are kind of narrow Gaussians, and we represent then this chi absolute square as a sum over such products of Gaussians. Now, the tricky part is that the full nuclear wave function appears also here in the denominator. And this if you work it out, for the quantum momentum leads to a coupling. Right? This is this term here, where the full product of Gaussians appears here. Now, this means if I want to calculate the quantum momentum that appears in the equation of motion that I showed you before on the ith trajectory, capital I is the index characterizing the trajectory, to calculate it, I need all the other trajectories as well. So this is why we call this algorithm a quantum classical coupled trajectory algorithm. So here as a first test, we propagate classical nuclei on the time-dependent potential energy surfaces. This is a case where we can solve the problem exactly. So we propagate on the exact surface. And you see very nicely the splitting of the nuclear wave packet is perfectly well described by the trajectories. More importantly, and this is a very important message now, if one plots a measure of decoherence, so this is essentially the off-diagonal elements of the electronic wave function in Born Oppenheimer basis. And we integrate over capital R. So it's a measure of decoherence. Then what we see here is that in the exact calculation, that's the green curve, this goes down. This is decoherence, as one would expect. But then in Ehrenfest dynamics and likewise surface hopping, you have this well-known problem that you have overcoherence. It does not decohere properly. Now, in our case, without invoking surface hopping, without invoking any decoherence corrections, we get decoherence. It's not perfect, but at least it's much better for sure than Ehrenfest dynamics and surface hopping. And it just comes from the fact that we are using the right classical forces here. Now, this was what I showed you, a model calculation, but this can also now be applied to real-world problems. And for this, we need to do something for the electronic equation. We do linear response TD-DFT for that. And then this is an application for the oxyrain molecule. And after laser excitation, you have a ring opening process. There's two competing mechanisms, either the oxygen moving to one of the carbons, or you have carbon-carbon stretch. And for this kind of real-world problem, it's a genuine ab initio calculation, one could call it. We can then make predictions which of the processes is more likely. And importantly, once again, this example is well known for the fact that decoherence is important. So in traditional methods, you only get it right when you add a decoherence correction to fused switches surface hopping. Surface hopping alone gives you this red curve. There is no decoherence. Only if you add a decoherence correction, you get it right. While our algorithm, the coupled trajectory mixed quantum classical algorithm, decoherence just comes out naturally without any additional effort. And this is implemented, I should mention, in the CPMD code. And so anybody can use it. So I will very briefly now talk about the vector potential. So there's another theorem that says that the total nuclear momentum and the total nuclear angular momentum, which is the expectation with respect to the full wave function, electron-nuclear wave function, with respect to, let's say here, the nuclear angular momentum operator, and you get it by tracing out all the degrees of freedom, can be calculated, once again, from the nuclear wave function alone. So the nuclear Schrödinger equation gives you that correctly. And then, knowing that, we can also look at the time derivative, use the Heisenberg equation of motion, and find something quite interesting, namely the Ehrenfest equation, if you wish, for the nuclear momentum and the angular momentum. Looks like this, where a force operator appears here that consists of two terms. First is a Lorentz-like force, one could say, which has an electric-like term, which is A dot minus the gradient of the scalar potential. And this Lorentz term, where B is the curl of the vector potential. But remember, the vector potential is not electromagnetic. It's more like this, yeah, it's like a Berry curvature. This is what this magnetic field does. So this is, knowing the time-dependent Schrödinger equation for the nuclei, this is what one probably would expect. But then there's an additional term, which is in blue here. And this is something weird. This is something that comes about from the fact that this vector potential is an n-body potential, an n-body operator. So you can, if you calculate the usual magnetic field from the vector potential, calculating the curl. If this is electromagnetism, the vector potential depends only on one coordinate vector with respect to which you take the curl. But here, A depends on the coordinates of many nuclei, so you can take also this curl with respect to another nuclear coordinate set. Right? And as a result of that, one gets some Lorentz-like force. This is again components of the velocity, but with different nuclei being involved. So this is an internuclear Berry curvature, one could call it. Okay, so this has no analog in electromagnetism. So these forces appear on one hand in the subsystem Ehrenfest equations, as I just showed you. They also appear in the classical limit of the nuclear time-dependent Schrödinger equation. So when or where in nature are they important? Well, I just give you one example, and this is from a molecular junction. If you apply a bias, then a battery, let's say, far away from this central region, where you have sandwiched a molecule in metallic leads, between metallic leads. Then if you switch on the battery, then an electronic current flows through the structure, and this electronic current then induces a force on the nuclei that leads to nuclear motion. And you can then have something like a water wheel. So imagine this water wheel, that this is an electronic current, and you kick the nuclei, and in this way, the nuclei can be turned into rotational motion. And this is called an atomic water wheel, right? So this molecule here in the middle may rotate. And this was described first by Todorov more than 10 years ago. Beautiful conjecture that was then also found experimentally. There's other effects. So depending on the geometry, this may be a rotational motion, but it may also be other nuclear motion that can lead to a breaking of the molecular bridge. And so this was the time-dependent case and the classical limit. And one more minute, and then I'm done. If you look at this vector potential, it also gives rise to something like an exact geometric phase. Well, now, as you all know, there is an analogous quantity, the Born Oppenheimer vector potential. Same expression, but with...
Did everyone lose audio, or is it just me?
Can you hear me? Hello?
Yes.
Yes, they can all hear.
Yeah. So then there is a Born Oppenheimer object. Whole books have been written about this. So this is a generic, genuine Berry phase. So it's adiabatic connotation. You move the nuclei, solve the Born Oppenheimer problem. At each fixed nuclear configuration, you go in a circle around the conical intersection, and you may gather this Berry phase. So infinitely heavy nuclei, you solve the Born Oppenheimer problem. While here, you don't do this. So this is not a Berry phase in the genuine sense. It just looks like it because this is a vector potential that has the same structure, but the electronic wave function is not the Born Oppenheimer wave function. It's the full thing. So we looked at this. So we wondered, are they the same, or how do they compare to each other? And we looked at this question in a model. It's known as Shin-Metyu model, where you have two heavy nuclei, and they're so heavy that you can fix them. And you have a third nucleus that is allowed to move around in the plane. And you have an electron that is also allowed to move around in the plane. So you have 4 degrees of freedom. And this you can still solve exactly. This is the Born Oppenheimer surfaces, and there's a genuine conical intersection here, and the Berry phase of pi is associated with it. So that's the Born Oppenheimer solution to the problem. But then we can, it's simple enough, also solve this problem exactly, look at the exact vector potential and calculate the geometric phase associated with the exact vector potential, and it turns out to be 0. Although in Born Oppenheimer, the geometric phase is pi. So how can this be? That it's a statement, if you wish, that in, at least for this particular example, the Born Oppenheimer Berry phase is really an artifact, right? Because the Berry phase is associated with infinite nuclear mass. So you move by hand the nuclei around the conical intersection, but real nuclei don't have infinite nuclear mass. They move the way they move. And in the real world, the real thing is this exact Berry potential that I showed you, and the geometric phase associated with this is 0. So does this now mean that we have to throw away all the books that have been written on the molecular Berry phase? For a while we thought that, but then we found another case where, in fact, also in the exact treatment, you find a non-vanishing Berry phase. It involves something like a circular motion. So this is so-called pseudo-rotation. I won't have time to talk about it, but this is the statement. And with this, I'm finishing. So here's the take-home messages. On one hand, the exact factorization is useful to settle conceptual issues. For example, to identify the unique force, the unique classical force on the nuclei, even in cases when the nuclear wave packet splits. Especially, there's this interesting Lorentz type force. And it also leads to an exact geometric phase. But the factorization can also be used as a starting point to develop practical algorithms. One was the quantum classical algorithm that I showed you, and the other one is treating in the electronic equation all the non-adiabatic effects in first-order perturbation theory. So that's it. Thank you for your patience.
Yeah.